Are our theoretical models wrong, or is it the universe? The answer may seem obvious, but recent findings from the James Webb Space Telescope, JWST, suggest otherwise. A series of mysterious discoveries now challenges the conventional cosmological understanding. What revolutionary knowledge can be derived from these impossible structures? Are our assumptions about the age and origins of the cosmos still tenable, or must we admit that we have been on the wrong astronomical track for decades? The exploration of the universe is a field of constant change. This evolution has led to many fascinating developments throughout history. Just think of our distant ancestors, who firmly believed that the Earth was the center of the universe around which all celestial bodies revolved. Today, of course, we know that Earth is just a tiny mosaic piece in a colossal overall picture that we have yet to decipher fully. And yet, every new discovery seems to challenge established ideas before they can be fully embraced. Take, for example, the work of Edwin Hubble. He recognized that practically all observed galaxies were moving away from us, indicating an expanding universe. Yet, Albert Einstein, clinging to his belief in a rigid, unchanging universe, introduced the cosmological constant to his field equations to maintain that view. Looking back, Einstein admitted his mistake, calling it the greatest blunder of his life. Hubble's observations, however, laid the groundwork for understanding the relentless expansion of the cosmos, which, according to current knowledge, began approximately 13.8 billion years ago with the Big Bang. Contrary to initial assumptions, the Big Bang did not involve a massive explosion into existing space. Instead, it marked the rapid expansion of space itself. From an original singularity, matter and time emerged from this tiny, hot starting point. But how can we be so sure of this today? The answer lies in looking backward at the universe's development. By calculating back to a point where the density of matter and energy becomes infinite, we arrive at the Big Bang. Supporting evidence includes the detection of cosmic microwave background radiation, a relic from shortly after the universe's creation. This nearly isotropic radiation fills the universe and corroborates the Big Bang theory. So far, so generally accepted. But what happens when discoveries arise that contradict the Big Bang theory and its foundational assumptions? Conventional cosmology suggests that the first stars formed 200 to 300 million years after the Big Bang and that the earliest galaxies were small, rudimentary structures. However, the James Webb Space Telescope has recently detected something that defies this framework: impossible galaxies. Astrophysicist Ivo Lab and his team at Swinburne University of Technology in Melbourne analyzed images from the JWST's near-infrared camera, NIRCam, under its early release program. These images, focusing on a section of the sky near the Big Dipper, revealed something extraordinary. Lab described his reaction. "I ran the analysis software, and it spit out two numbers: distance 13.1 billion years and mass 100 billion stars. I almost spit out my coffee. I knew we had just discovered the impossible, impossibly early, impossibly massive galaxies. The existence of these galaxies presents a profound dilemma. To explain their presence, either the density of matter in the young universe must have been 2 to 5 times greater than current models predict, or these galaxies must have formed through entirely unknown mechanisms. In either case, our understanding of the cosmos requires a fundamental shift. Within 500 to 700 million years after the Big Bang, 6 galaxies with masses comparable to or exceeding the Milky Way's were already in existence. This challenges the prevailing assumption that galaxies began as small clouds of stars and dust that gradually grew over time. Dubbed universe breakers, these galaxies call into question what was previously considered scientifically certain. The mass of stars in these early galaxies is up to 100 times greater than old models suggest. Until now, cosmology posited that galaxies formed gradually, growing from small, simple structures. But could there be alternative pathways to galaxy formation? This discovery deepens the mystery surrounding the universe's early stages, leaving scientists searching for answers. The JWST's next major discovery further underscores the need to reevaluate our models. Researchers from the Scuola Normale Superiore in Pisa identified JWST 13-0, the oldest known galaxy, using data from the telescope. This galaxy formed approximately 290 million years after the Big Bang. Analysis indicates that it likely took only about 100 million years to grow to its observed size. Yet this structure was not a faint, nascent galaxy as current models would predict, but a massive entity containing several hundred million solar masses of stars. How could such a bright and massive galaxy form so quickly in the universe's early phase? Moreover, the galaxy's spectral analysis revealed the presence of oxygen and hydrogen emission lines. This indicates that multiple generations of massive stars had already completed their life cycles by the time scientists observed the galaxy. Once again, the question arises, how could this have happened in such a short period? Despite these perplexing findings, not all discoveries lead to dead ends. The James Webb Telescope has provided insights into another long-debated topic: how light emerged in the early universe. Around 380,000 years after the Big Bang, during the so-called Dark Ages, the universe was a dense fog of neutral hydrogen gas. There were no stars, no galaxies, and no light sources. This began to change roughly 100 million years later during the era of reionization, when the first energetic stars ionized the hydrogen gas, making the universe translucent. The origin of the photons that lit up the cosmos has been a contentious issue for decades. Some theories pointed to black holes as the source. However, the JWST has now lifted the cosmic veil to reveal that small dwarf galaxies likely produced vast amounts of high-energy radiation. An international research team tracked this phenomenon as part of the Uncover program, using the telescope's NIR-SPEC and NIR-CAM instruments. To observe these distant galaxies, researchers employed a clever trick, the gravitational lens effect. This phenomenon occurs when large masses, like galaxy clusters, bend the light of distant sources. The closer the light passes to the mass, the more it is deflected. In this case, light from faint galaxies was magnified by the galaxy cluster Abell 2744. This allowed researchers to identify 8 small galaxies emitting 4 times more radiation than previously assumed. These dwarf galaxies, though faint, played a critical role in the early universe. They are representative of the low-mass, high-energy structures that likely dominated the cosmos during the era of reionization. While these 8 galaxies did not single-handedly reionize the universe, they exemplify the type of structures that collectively transformed the cosmos, making it transparent. The discoveries from the James Webb Space Telescope highlight the dynamic and ever-changing nature of cosmological understanding. They challenge long-standing assumptions and open new avenues for exploration. As we continue to unravel the mysteries of the universe, one thing is clear: each new discovery not only deepens our understanding but also reminds us of how much we still have to learn. The discoveries made by the James Webb Space Telescope, JWST, have sent shockwaves through the scientific community, pushing the boundaries of what we know, or think we know, about the universe. Each new observation seems to carry profound implications, forcing researchers to revisit fundamental assumptions about the cosmos. Beyond merely uncovering impossibly massive early galaxies or pinpointing the universe's oldest structures, these findings reveal that the universe's formative years were far more dynamic and complex than previously imagined. One of the most striking aspects of these revelations is their impact on the timeline of cosmic evolution. Our current models rely on a stepwise progression, where the first stars formed in small groups, eventually coalescing into the primordial galaxies we observe today. This slow, methodical process was thought to have taken hundreds of millions of years. The JWST's findings, however, paint a dramatically different picture: colossal galaxies, brimming with mature stars, existing just a few hundred million years after the Big Bang. This accelerated development not only upends timelines but also challenges the mechanisms by which stars and galaxies form. Current cosmological models are underpinned by the lambda cold dark matter (lambda CDM) framework, which assumes that dark matter played a critical role in the formation and clustering of galaxies. In this model, dark matter served as a gravitational scaffold around which baryonic matter, ordinary matter like hydrogen and helium, could accumulate. The unexpectedly massive galaxies detected by JWST, however, suggests that either the role of dark matter was significantly underestimated or that entirely new processes were at play. Could there have been a form of star formation or galaxy assembly that we have yet to understand? These questions highlight the gaps in our current knowledge and underscore the need for new theoretical models. Another intriguing consequence of these findings is the re-examination of star formation rates in the early universe. The presence of heavy elements like oxygen in these ancient galaxies implies that massive stars lived and died in quick succession, enriching the surrounding gas with heavier elements through supernova explosions. This rapid recycling of matter contradicts traditional star formation theories, which assume a slower pace in the early universe due to lower temperatures and densities. If stars were forming and evolving much faster than predicted, it raises questions about the energy sources driving such rapid processes. Could exotic physics or early supermassive black holes have played a role in catalyzing this extraordinary evolution? Thanks for watching Space Lab. Don't forget to like, share, and subscribe for more cosmic discoveries. Keep exploring, and we'll see you next time.